Good day, everyone, wherever you are in the world. This is a new experience for all of us, and while I'm glad we can all be here virtually, I hope it does not become the norm. I hope you're all safe and well. Most of my recent talks have focused on problems in shape generation, how to train generative models of 3D geometry, especially in a structure-aware way. We organized a separate CVPR workshop on this topic, and I encourage you to look at our recent Eurographic star on the subject as well. However, I am also interested in discriminative problems, so I thought I would take this nice opportunity to talk about some of the work we've been doing on one of the most classic discriminative problems of all, shape segmentation. While segmentation is a well-studied topic, most state-of-the-art methods train on huge amounts of human annotated data. In the broad vision space, there are entire companies which exist to provide large-scale annotation services. In this talk, I will present some ideas on how to achieve competitive segmentation quality with less and less human effort and expense in gathering supervision. Let's start by defining the shape segmentation problem. Our goal is to assign a label which may be meaningful, such as head or leg, or abstract, to each point on a shape so that different parts of the shape may be distinguished from each other. In the 3D setting, we usually discretize the continuous shape as a polygon mesh, or point cloud, or voxel grid, and assign a label to each atomic element in this representation. It turns out that handwritten heuristics for assigning labels, in other words, for clustering or classifying the elements, are limited in capturing the variability of part shapes. So even in the traditional or pre-deep learning era, statistical learning from segmented exemplars was the best general approach for segmenting 3D shapes. A canonical representative is a mesh-based conditional random field where a classifier assigns a label independently to each mesh face, and a graph-based optimization with learned edge weights regularizes the distribution so that similar adjacent faces get similar labels. With the advent of deep learning, we can try to take the same general setup but replace the traditional shallow classifier with a deep network. We presented an oral at CVPR 3 years ago on using 2D networks in such a setup to segment 3D shapes. The key idea is that we can render the shape to a collection of images, segment these images, and aggregate the results after projecting back onto the shape. Thus, we can take advantage of the generally more advanced architectures of 2D networks, as well as the availability of much greater image data for pre-training. In more detail, the unity term of our conditional random field is computed by a collection of fully convolutional image convnets with shared weights, which process adaptively selected rendered views of the object on the left. The segmentation of each view is projected back onto the shape surface and the results aggregated by pooling. Finally, a graph-based optimization is implemented as a network layer to regularize the segments with learned edge weights, producing the final segmented and labeled output on the right. The whole setup is trained end-to-end. Projective networks turned out to be tremendously good at segmenting shapes, even though the bulk of their processing happens entirely in 2D. There are a lot of numbers on this slide that I don't expect you to digest in one go, but for a quick takeaway, look at the summary statistics in the small table on the right. The segmentation accuracies of competing state-of-the-art methods are circled in blue, and our accuracies in red. As you can see, our results are better by a large margin. Further, projective nets are fundamentally representation agnostic, which means they can natively process any shape representation that can be rendered. Of course, the surface-based CRF layer would need to be adapted, but the gains from this layer are actually quite small. As a fun factoid, after we published a follow-up paper on 3D dense correspondences, there was a time when I think projective nets had the best benchmark performance on all three of the classic shape analysis tasks: classification, segmentation, and correspondences. So all this seems fine and dandy, but this performance comes at a cost. This network and other contemporary methods are trained on large collections of carefully segmented and labeled training shapes. Such annotated collections are difficult, time-consuming, and expensive to build. Hence, a natural question is, can we reduce the amount of annotation effort by training our models with less supervision? The answer happily turns out to be yes. In this talk, I will present our work over the last 3 years that trains highly performant segmentation models with dramatically less supervision. This reduced supervision falls under 3 main themes. The first is weak supervision, where training shapes have incomplete annotations, for instance by providing only shape-level tags but omitting any region markings, or providing inconsistent, unlabeled training data from which a consistent segmentation model must be inferred. The second theme is one-shot supervision, where a single segmented and labeled shape constitutes the entirety of the annotations. We do assume that many unannotated examples are also available, for instance, as a batch of test shapes. Finally, we study the completely unsupervised setup, where only a number of completely unannotated shapes are available. Note that these cases fall on a spectrum. As we reduce the amount of supervision, annotation is easier, but the control of the output becomes harder. This trade-off is a design choice to be made for the particular task at hand. I'll first talk about work we presented at CVPR 2 years ago on segmentic shapes in a weakly supervised binary labeling setup where the presence or absence of labeled parts is indicated only with shape-level tags. No regions are explicitly marked on any of the training shapes. For instance, in the shapes shown here, the beige chairs possess armrests while the green chairs do not. The beige chairs are tagged with has armrest and the green chairs are tagged with no armrest. From just this information, the segmentation algorithm must infer what armrests look like. The process can be thought of as a subtraction operation. If we imagine somehow geometrically subtracting the green shapes from the beige ones, what will be left will be the armrests. However, because of the great geometric variety in such a collection, the shapes are not in correspondence and actual Boolean subtraction does not work. Instead, we will use a deep network to do what might be called statistical subtraction. We called the network we designed for this task WooNet because it chains 3 voxel UNets together. However, the architecture has significant differences from a stack of 3 standard UNets. First, each of our U's is quite shallow, doing just a single level of down and up sampling. Second, the network has skip connections not just between high-resolution layers, but also between low-resolution layers. The output of this chain, which is the same resolution as the input, is branched into 2 segmentation maps, one for voxels possessing the query label and one for voxels lacking the query label. Note that under weak annotation, we do not know the ground truth voxel labels in advance. We only know the shape level tag. Hence, we globally pool the label probabilities in each map to estimate the tag for the overall shape. In other words, the final layer is a shape level classifier that predicts the probability of the entire shape having a given tag. It is trained with a cross-entropy loss. Since the classifier output depends directly on the segmentation maps without intermediate network layers, the hope is that the classification will be correct if and only if the voxel labels are also approximately correct. Here are some examples of weakly supervised binary segmentation with WooNet. On the top, we marked airplanes as possessing or lacking wing structures like propellers and engines. In order to correctly predict these tags from the voxelized shapes, WooNet correctly identified the locations of the distinguishing parts marked in red. Similarly, the cars at the bottom were marked as possessing or lacking roofs. Again, WooNet correctly identified the roof regions marked in red. Here are further examples of weakly supervised segmentation with WooNet for detecting backs of chairs, sails of ships, heads of beds, and swivel legs of chairs. In most of these cases, there are errors in the segment boundaries, even though the parts are correctly located. Note, however, that WooNet has no regularization or part priors at all. It is merely learning to detect the minimal regions that can serve to distinguish between the 2 tags and are also roughly consistent across shapes. It does a good job on this front, but with better regularization and priors, as we will see in some of the subsequent slides, we can do better. Here are some quantitative examples of the performance of WooNet as precision recall plots. The left figure shows ablation studies, the middle figure compares to single and stacked deep UNets, and the right figure compares to the prior work of Schillen and Funkhauser, who used a spiritually similar setup but with classical machine learning models. In all of these figures, the red curve represents WooNet and higher curves are better. As we can see, our method significantly outperforms alternatives in all cases and is a sort of architectural sweet spot. Greater insight as to why this is so comes from digging deeper into the comparison with regular UNets. Here is a visualization of actual information flow in a deep voxel UNet. The input is one of the 4 shapes in the top left, whose features are progressively downsampled all the way down to the very low resolution bottleneck and then upsampled back up to the original resolution. Skip connections span the 2 arms of the U. In all cases, redder or warmer colors represent voxels possessing the query label, and bluer or cooler colors represent voxels lacking the query label. The output segmentation map under weak supervision is on the top right. If we trace the changing segmentation maps through the layers, down the left arm, through the bottleneck, and up the right arm, we can see that the segments are relatively correctly localized in the bottleneck, but this localization is rapidly lost, probably as a result of over-summarization, low field of view, and no further summarization of the concatenated signals. In contrast, here is information flow for the same shapes in WooNet. Note how the network locks onto the distinguishing part and refines it in successive U's. Shallow UNets prevent over-summarization, and skip connections at both low and high resolutions allow iterative summarization where previous summaries directly influence subsequent ones at the same resolution. The final output on the right has much better localization of the distinguishing parts. Okay, so we looked at one type of weak supervision where shape tags are provided but not region annotations. Now we look at a different weakly supervised setup where we are provided with segmentations during training, but these segmentations are inconsistent with each other, varying in part counts, granularities, and grouping. Further, they are unlabeled or at least lack useful and consistent labels. This setup is common in many standard 3D mesh repositories, and the goal is to learn a model that can consistently co-segment a set of test shapes. This is similar to an unsupervised problem, but we can exploit 2 key observations. First, we can train a weak prior for what parts may look like using the inconsistently segmented dataset for training. This prior cannot distinguish between different part types or between different granularities of parts. All it can do is to decide if a proposed segment looks like some real part it has seen before and predict how to refine it to improve its plausibility. Second, we can explicitly optimize for consistency across the segmented test set. This is a non-decomposable loss which is not easy to design. In an oral paper we presented 2 days ago at CVPR, we showed how to combine a weak part prior with a consistency loss in order to co-segment a set of shapes. Note that the final segments adapt to the provided test set. The same shape, as in the case of the chair circled in red here, is segmented differently depending on whether it is in the test set on the left or in the test set on the right. Nevertheless, both segmentations are plausible. Our method, dubbed AdaCoSeg, has 2 main modules. The first learns a weak part prior from inconsistent and unlabeled segmentations. I will not discuss this in detail because of lack of time. The main takeaway is that this prior is a denoising module that takes a roughly segmented part and tries to refine its boundaries to make it more plausible. The more interesting module is the actual co-segmentation network that is optimized iteratively at test time to jointly predict consistent segmentations of test shapes. This network reuses the pre-trained part prior and optimizes a novel consistency loss circled here in red. Let's look at the co-segmentation network in more detail. The input set of test shapes, represented as point clouds, are individually processed with a per-point classifier that assigns one of k abstract labels to each point. K is a hyperparameter of the network chosen by the user to represent the maximum number of parts a shape might have. The resulting segments, each consisting of points with a single label, are refined by the pre-trained weak denoising prior to make them more plausible. Feature vectors are then computed for each denoised part using a module pre-trained along with the denoising prior. Finally, the part feature vectors for each label from all the test shapes are assembled into a matrix for that label. Our consistency loss is defined over these matrices. The intuition is that if the shape segmentations are consistent with each other, parts with the same label should have similar features, and parts with different labels should have different features. Thus, the matrix of part features for a single label should have low rank, and the matrix concatenating part features for two different labels should have high rank. Our loss function directly expresses this objective in terms of matrix ranks. Since exact ranks are harder to use within a network, we use the second singular value of a matrix as a proxy for its rank. The initial segmentation maps are iteratively optimized by training the network with this consistency loss. Now let's look at some results. Note again that the weak part prior is trained on an inconsistently segmented and unlabeled training set obtained from real-world mesh repositories as visualized on the top left. There is significant variation in both part counts within a domain, shown in the histogram, as well as the exact segmentations for a given part count, shown for some example shapes. As a first example, observe that AdaCoSeg can improve the segmentation consistency of its own inconsistent training data. Given training shapes such as the ones in the first and third rows, AdaCoSeg consistently resegments the shapes as shown in the second and fourth rows. This is borne out quantitatively. The RAND index of segmentation quality improves, that is to say, reduces, after processing the shapes with our network. Here are more co-segmentation results for a variety of domains. Note the high consistency between segmentations and the plausibility of individual segments despite the high variation in shape geometry and topology. We compared our method to unsupervised techniques and observed a statistical improvement in nearly all cases. Note that this comparison is not entirely fair, since the other methods are fully unsupervised, whereas we leverage an inconsistently segmented training set in order to learn a weak part prior. Still, it shows the benefit of adding a little bit of freely available weak supervision in conjunction with a consistency objective. Okay, can we get away with even less supervision? In work published at the last ICCV, we showed that this is possible with carefully selected network architectures. In particular, we studied networks that compute implicit fields for shapes, 3D scalar functions with level sets which are 2D surfaces of target shapes. These scalar fields are commonly either occupancy functions, which are 1 inside the volume of the shape and 0 outside, or sign distance fields, which are negative inside the shape and positive outside. Implicit field-based networks have become a hot topic in geometry processing and visual data compression in the recent past, as demonstrated by the two initial talks of this workshop. While many of the attention-grabbing applications are generative or at least representation-related, it turns out that implicit field networks have nice properties that make them useful in discriminative contexts as well, such as for shape segmentation. The key aspect of an implicit field network is that it outputs the scalar value for a single query point at a time, reducing its architectural complexity and sharply focusing its resources. Here's a representative version of an autoencoder that encodes shapes as implicit fields. A global feature vector is computed to identify which shape is being encoded using some standard architecture such as a voxel CNN. This feature vector is concatenated with the x, y, and z coordinates of a query point and processed through a small number of typically fully connected layers, resulting in a single scalar value for the implicit field at the given point. To reconstruct the shape, the network is repeatedly queried over a volume to build an occupancy map. This map is compared with the input in order to compute a reconstruction loss to train the autoencoder. To perform unsupervised segmentation with an implicit field autoencoder, we use a trick similar to the one we used for WooNet. We introduce branches at the final level of the network, where each branch will reconstruct different parts of the input. We call this branched autoencoder BAE-NET. The branches need not have meaningful labels. They may be assigned only abstract labels for the unsupervised case. Each branch produces a scalar value. These values are max pooled across branches to produce the final scalar output. The magical part is that nothing else about the network changes. The loss is still the same reconstruction loss, and there are no other cues to the network indicating what segments are good and which ones are bad. If the architecture is carefully chosen to be extremely simple and shallow, the network is forced to use each branch to identify a single type of compact, consistent part across the shape collection. The branches can be queried across an input shape to build up the final segmentation map. Let's look at BAE-NET in action on a 2D example with a pixel grid replacing a voxel grid. The input images are combinations of 3 primitive shapes in different relative positions. A 4-branch BAE-NET accurately isolates the 3 constituent shapes, which are then recomposed to compute the reconstruction loss. Note that BAE-NET has not been pre-trained with any examples of these primitive shapes or any other shapes, and the shapes themselves are heavily overlapping in several of the examples. How then does the network do the segmentation? The secret is the extremely shallow decoder architecture with just 3 fully connected layers. The network is forced to work with these rudimentary resources, and it turns out the economical option is to reconstruct one fixed primitive shape in each branch. If we visualize all the training images in a 3-dimensional plot, where each horizontal slice represents an input image, the network can be thought of as sorting the input along the vertical axis in order to create simple prismoidal structures with fixed cross-sections that can then be encoded even with a tiny network. If you look at the activation maps of the 3 layers, top to bottom, we see half spaces captured in the first layer and only slightly more complex combinations in the next 2 layers. The network cannot represent complex distributions and is forced to be smart. Let's turn to some real 3D segmentation tasks. The same setup applied to unsupervised 3D segmentation produces very high segmentation accuracies with 0 supervision. Undoubtedly, we are taking advantage of the fact that benchmark datasets actually have fairly simple coarse segmentations. Segments can be carved out of the shape using simple compact 3D volumes, which the network can represent effectively. It's easy to add a small amount of strong supervision to the mix. If we add one single fully segmented and labeled training example to the otherwise unannotated collection, the point labeling accuracy is in the high 70s. This is significantly better than state-of-the-art segmentation methods trained on 10% of their regular training dataset with an average of 765 shapes per category, and remains better even when the competing methods are trained with 20% of their datasets. Note again that the entire annotation for BAE-NET in this case is a single strongly supervised shape. 2-shot and 3-shot training produces further improvements. Finally, we note that BAE-NET also produces state-of-the-art results with weak supervision in the form of shape-level tags. Okay, so what are the takeaways from this work? First, the obvious conclusion is that single shape coarse segmentation on current benchmark datasets can be done with a great deal of accuracy using extremely little supervision, whether it is weak, 1-shot, or 0. Our work provides some first steps which are already quite performant. More challenging segmentation benchmarks have been and are being prepared, but it is tempting to think that our networks already have far more capacity than strictly required for extracting compact, consistently spatially located, well-isolated part categories from everyday shapes. We just need to focus that capacity effectively. Secondly, the structure of the network is increasingly important as we use less and less supervision. This was dramatically demonstrated with the deep image prior work from a couple of years ago, where the structure of a completely untrained standard network was a strong enough prior for state-of-the-art image denoising and completion. Our experiments with the shallow decoder of BAE-NET suggest similar lessons. I think there is excellent potential for work that reduces the human annotation load for standard tasks while retaining control over the accuracy and diversity of the output. Optimizing both of these opposed objectives is challenging. Other promising avenues for future work include making shape processing representation agnostic, as we did in our Shape Unicode paper from last year, where we showed that a single segmentation algorithm could process any input representation of shapes, be it point clouds, voxel grids, or images, by operating only on a shared representation-agnostic latent space. Finally, I personally feel that improving the quality of segmentation boundaries, an objective not well captured by standard losses or evaluation metrics, would have major impact on several applications in graphics. With that, I think I'll stop here. I'd like to recognize the hard work of the lead student authors who made these advances possible. These are really their papers. The rest of us just come along for the ride and chip in where we can. So a big shout out to Sanjeev, Chenyang, Zhichin, and Kangshui. I've listed the 3 papers I focused on here. Do check them out at your leisure. We'd be glad to hear any feedback or suggestions from you. Thank you very much. Thank you to the organizers, and I hope to see you all in person at some point.